Yeah.
See you right.
Yeah.
So it's just the agenda.
Kannst du auch mittweeten.
So welcome everyone to the second Kubernetes meetup here in Cologne. This time we're at Rewe Digital. Thanks for the location and for this awesome food and all the drinks. The agenda for tonight. So we're a little bit late, but no worries. We've got plenty of time. So we've got Ed Harrison tonight from Project Calico. We will be talking about secure cloud-native networking. Afterwards, we'll have some short break, can grab some drinks, have some food, and I will just give some 15 minutes wrap up from KubeCon, which was last week. And then we have some more time for networking, whatever you want. So please welcome Ed to the stage.
Maybe. Oh, it's my daughter, so that's a good start.
Starting from scratch.
Aha, right.
There we go.
Great.
So big old round of applause for Ed, please.
Good evening. Hi. As Daniel said, my name is Ed Harrison, and I work for Project Calico, which is an open source networking project for containers and VMs and things like Kubernetes. Daniel asked me about 4 or 6 weeks ago whether I'd like to come to Cologne to do the meetup, and I thought, yeah, great, opportunity to talk about Calico. That's a great idea. When I bumped into him on Friday at KubeCon, I had a sudden worry. I said, you do realise I don't speak German, and is that going to be a problem? And he assured me it wouldn't be. So I do apologise that I don't speak any German and I'm doing this in English. But if that's a problem, now is probably the time to leave. But also, if I speak too quickly or you want me to slow down at all, do just shout out or throw something at me, and I will do my best. So I'm going to talk about, say, simple, scalable, secure networking for Kubernetes. My notes are all the way over there, so if I get a bit confused, that's kind of why. We had some HDMI cable problems. I've also been not feeling so great, so if I collapse coughing, please bear with me, but fingers crossed. So first of all, networking. Why do we care? Well, I think in the old days, when I first started looking at playing with computers, you had an application. It didn't talk to anyone else. Let's face it, it was normally a game, and it just sat on its own. These days, we've moved on from that. So applications tend to want to talk to the internet. Pretty much impossible to get anything on your phone, for example, that doesn't fall to bits if it doesn't have an internet connection. But there's more to it than that. In the world of Kubernetes and microservices, we've also got the case that, well, you don't just build everything in a single application anymore. Your application may be relying on some other service, so there's some more networking involved there. You might have another application that's relying on the same service, so you're sharing services between applications. Again, networking is important. That's all running on one host, but you have other services on other hosts. Again, Kubernetes, that's the whole idea. You've got lots of compute resource and you put your pods wherever you want them, and you need to communicate between them. More applications. Maybe you get services or applications where you don't want them to communicate with everything. So you've got to start worrying about security policies. But you do want them to communicate with other services and other applications. So hopefully, you're all here and bought into the idea that networks are important. In the cloud-native landscape, and a good network is something that you do need. Okay, so I'm going to talk about 3 main areas of 3 main things you want to look for in your networking solution. The core pillar that all of this is built on, though, is IP. We're starting, these days, we're starting from the basis that If you're writing applications, you're using Kubernetes, you're writing cloud-native applications with microservices, they're not going to communicate over AppleTalk or NetBIOS or IPX. They're just going to use IP. You know, most applications these days use REST APIs. It's just IP connectivity. So that's the sort of core pillar that we're starting from. You don't need anything more complicated than IP. Yeah, the fabric in your data center is probably running over Ethernet, but all you're running over it is IP. Okay, so with that out of the way, the first thing I'm going to talk about is operational simplicity. So, what is this? This is to provide an example. One of my friends, the main architect for Calico, worked, a few years ago, he worked at a bioinformatics company. So doing stuff with DNA and things like that. They weren't using Kubernetes, this was before Kubernetes days. They were using OpenStack. So some of you may think, well, that was their first mistake when getting to the story, but we'll see. But anyway, they were doing an upgrade of OpenStack. They had a working system, they had hundreds of VMs talking to each other. They wanted to upgrade from one version, I think it was the Essex release of OpenStack, to the Fulsom release of OpenStack. So it's a few years ago. They did the upgrade, and all their networking fell apart. VMs could no longer communicate to other VMs, and it was all a bit of a disaster. Now, Christopher is a networking expert. He's worked for 20 years building and running IP networks. He's built transatlantic IP networks, when he worked for Telstra. He knows IP. So he thought, fine, we've got a networking problem. How hard can it be to debug? Sat down, looked at it, tried the usual things, ping, trace through. Yeah, could kind of see, okay, well, packets are getting this far and then something's happening. Again, how hard can it be? 36 hours solid work later, he still couldn't work out what was going on with the system, and they had to roll back their upgrade. Yeah, and as I say, this is someone who knows how to debug network problems. And the reason it was so complicated, and the reason he couldn't do it, is because of stuff like this. Okay, so this is in OpenStack, and this is a page out of the OpenStack networking manual. The big box is one compute host. That's one server. The bits at the top are VMs. This is your network at the bottom. To get a packet from here, out of here, there's quite a lot of little stages that you're going through before you end up getting encapsulated on a VLAN or a VXLAN. And it's things like this that was why he couldn't understand what was going on. It wasn't the case that I'm sending an IP packet from VM1 to VM5. I should just see an IP packet flowing. It was going through all of these layers, all of this complexity, and that caused the problem. And he sat there and thought, there must be a simpler way. We've built IP networks before. Surely we must be able to build them in a virtualized or a containerized world without having to jump through all of these little pieces. And he sat back and thought, well, what sort of IP networks have we built that have worked? And he thought of the internet. Now, this isn't actually the whole internet. This is only a little bit of it. But the idea is, you have hosts. They have an IP address, and they run some stuff. And your hosts are connected to routers, and routers are connected to each other. And through the routers, addressing information is propagated around the network using routing protocols. And through that mechanism, you get the fact that this guy over here wants to send an IP packet to this guy over here. Forwards it out, this router knows, oh, well, the next hop is down here. This router knows, oh, you're going over to 172.19.1.3. Oh, you need to go over here, and so on. And scale that up, that's basically how the internet works. And he thought, well, that's all I'm trying to do with my VMs or my container. So can we not use something similar? So, same picture, let's just draw it down a level. Now, this box here is your container host. So each of these boxes is a container. But again, the key thing is give each one an IP address. and then run some stuff. Connect them into a router, connect the routers together, distribute traffic, job done. Everyone can, container over here can reach container over there because it's just routing an IP packet, and we know how to do that. It's great that Kubernetes has already always had the idea of one IP per pod. A lot of other container technologies didn't even get that far. And, just one IP per host, use some port mapping, it'll be fine. Yeah, no, it's not fine. But that's the basic idea, and that's what we're doing in Calico. So in the Calico situation, so this is your container host. You've got a couple of containers, they're in their own container namespace. So they have interfaces, and those interfaces feed into the sort of root namespace, and in particular they feed into the router that happens to sit inside the Linux kernel. You have this already. If you've got a Linux box, it has a router. It has a very good router. The Linux kernel, we've done testing. We've thrown 500,000 roots into the Linux kernel. Doesn't really notice it. Quite happily route traffic, until the cows come home. So this is one of the basic ideas behind Calico. Just have a rooted address to each of your containers. So, containers on the particular host, so 10.0.0.1, in the routing table, we say 10.0.0.1, you can reach that through Cali 34, there you go. Containers on other hosts, we pull into the routing table through, for example, BGP. So here, say 10.0.1.0/26, if you're trying to get to that, that CIDR, then this is your next hop, and that's your device, i.e. send it out the box, route the traffic out the box, and then the next hop will work out how to, how to get it to the destination. So it's simple, and the key thing is when you're sending an IP packet in a network like this, what you're seeing is an IP packet. It's not being encapsulated, it's not going into a tunnel, it's just an IP packet that's being routed hop by hop until it hits the destination. So in Chris's case, if he's trying to debug a problem, well, he can do ping. That didn't work. I'll do traceroute. I can see, oh, hold on, it's getting to this, it's getting to this router here, or it's getting to this host here. Something's going on there, and then you can identify what's going on. There's nothing special, there's nothing magic going on. It's just an IP packet. So, that's the first sort of idea, operational simplicity. When you're looking for a networking solution, at some point you are going to have to debug it. So you want it to be as straightforward as possible to do that debugging. The next thing to talk about is scalability. Who can tell me what this is? There's a free fluffy cat for whoever can tell me what this picture is. What?
Density.
Sorry?
Density of circuits on the CPU.
Yes, kind of reading the thing, but it's a famous. Moore's law. That's the one. There you go. So you set him up, but he got the word. Yeah, this is from. You'll get another chance for a fluffy cat later. It's fine. So this is from Gordon Moore's seminal paper from the 60s of that we all know. Computing power is basically going to get cheaper. So what this is showing is this sort of sweet spot for each year is moving off to the right. So that means the sweet spot is where it's the most efficient to build your circuit, your printed circuit. So it's moving over to the right, which means we're getting exponentially more circuits, or more components per circuit. But as time goes on, it's also moving down, which is the cost. So things are getting exponentially cheaper. Okay, so what does that mean? Well, in effect, that means this. Stuff is cheaper. If you look at Amazon, it's now under half, to get the same sort of instance and same computing power. These days, you can pay less than half of what you were paying 4 years ago. And that has a couple of effects. For a start, it means that people are using their computing resource more profligately. maybe, i.e., if computing resource is cheaper, well, let's spin up more containers. Let's have more redundancy. Let's use it more. Use that price saving by firing up more things. And as you fire up more things, your network gets more complicated. Back in the day where you just had a single server, well, each server had one IP address. We had that on the picture. When you started looking at VMs, maybe a host running some VMs, you might have put 10 VMs on a host. So you now need 10 IP addresses for that host. With containers, we could be talking 100 containers per host or more. And suddenly the complexity of the networking that you need is scaling as the price is coming down, as you're doing more with your computing resource. So you need a network that can actually scale like that. And that's the other point. You're trying, because the computing resource is doing more, and as we're moving into things like Microsoft, you're just using more. You're saying, well, I'm going to fire up extra containers, and I need to network in between them. It's kind of what we said at the beginning. Networking is important. We're using more of it. This is where, if I was close to my notes, I'd think about what I was going to say next. But yes, I know what I was going to say next. It's a short video. So this is an example. So we're talking scalability here. So this is an example from one of the tests that we do with Calico. And what we're doing here, we have 500 compute hosts running on GCE, so in Google Cloud. And what we're trying to do is start up 100 containers on each. But not only start them up, network them together and apply the security rules that Calico enforces. And what we're doing here, we're trying to start up 50,000 containers in 5 minutes. So it's around 150, 160 containers per second. And the key thing that we want to make sure is that it's no good starting up a container, but if it takes 2 minutes for its network to actually come up and the security to be programmed, that's no good. So what we're doing here, we're measuring what we call the time to first ping. So what this is saying is 50% of the containers have a time to first ping of less than 2 milliseconds. 99% of them have a time to first ping of less than 10 milliseconds. And that time to first ping is literally the container's job in this test was, as soon as pip1 starts, it's going to try and send a packet out to another container that's previously been started. And it's going to time how long it takes for that result to come back and then record it. And in order for that result to come back, the networking needs to be up. So the IP address reachability of the new container needs to have been programmed around the fabric. But more to the point, as I said, we've got security rules in place here as well. And in Calico, until you've programmed your security rules, you can't talk to anyone. So it's kind of like deny everything until I've got new rules in place. So those security rules need to have been applied as well. And what we're seeing is, even with all that work going on across 500 hosts with 50,000 containers in the system, even right at the end of the test, we're still getting containers coming back within, I'd say 99% of them were under 10 milliseconds, 50% of them under 2 milliseconds. So the point, the real point I'm trying to make here is, even if you're not thinking about scalability now, if you're working with Kubernetes, you're working with microservices, maybe you're just starting out on your journey in this direction, at some point, you probably are going to want to scale to these sorts of levels. If your project is successful, you'd want to hope that, we really are firing up, hundreds web front ends or whatever for this application because we've been successful. And you want to be able to make sure you're choosing a networking sort of infrastructure that can, that can support that level of scalability and that level of churn. In particular, when you're talking auto-scaling of applications, you may be firing up 100 containers in the time it takes for an ad break to come on TV because you happen to know, oh God, our advert's going to come up. We need to fire up a whole load of new web front ends for 5 minutes because the ad break's going to be on. We're going to hit a lot of traffic, and then we're going to scale them back down. If your networking infrastructure can't spin those up and get them reachable in the time you need, then you're in trouble, or you're going to spend a lot more money on resource because you think, better fire them up an hour in advance just in case, to make sure everything's there. Okay, final pillar, and I'm going to spend more time talking about this, is security. So, back in 2014, November 2014, the folks who worked for Sony Pictures arrived at work and saw this on their desktops. At first they thought it was a new PS4 game, but it turned out that it was worse than that. The Sony Pictures network had been hacked. By the time the IT department was able to shut down the malware that had been released, something over 50% of the servers that Sony had been wiped clean of all their data. And 80% of the desktops were displaying this. You probably saw it in the news. It was a big deal. And that'll teach Sony to make nasty pictures about North Korea, but there you go. When the FBI looked into it, one of the things that they came up and said is this quote that I've highlighted here. Once the invaders made it past the network gates, they could go anywhere they wanted because Sony hadn't locked any doors. I kind of like thinking about this as the armadillo model of security. So it's very hard shell, it's quite hard to penetrate inside, but once you get past that hard exterior, you've got access to all of the lovely gooey middle, assuming armadillos are your thing. Putting it a slightly different way. If you imagine this as, again, a small corner of the Sony network, once the attacker had got in here, he could do anything. He could get anywhere. They reckon that the initial sort of attack into Sony happened months before that thing appeared on everyone's screens. So, it wasn't just, they happened to get in there and then they released the malware. They spent months wandering around the Sony network, stealing all of the the data, the emails that got thrown up on the internet, and to embarrass the executives and stars. And no one knew. It wasn't until that big malware release that I thought, oh my God, something's happened. But actually, the breach happened months before that. Okay, so that doesn't necessarily relate directly to containers and Kubernetes, but let's bear with me for a bit. Does anyone remember this kind of approach, the 3-tier application? So this was the case, this is where you've got your web front end, you've got your back end logic, and you've got your database. And the typical way in which this would be put together, your IT department back in the day would say, fine, we've got this particular class of server which we're going to use for our database, particular type of hardware that's going to be database. We've got different hardware which we're going to put in for the back end, and then some different hardware again for the front end. And what we're going to do, we're going to put firewalls between them all. Everything's great. This reminds me a bit like the armadillo, but of more of this sort of medieval city idea. So you've got your wall around the majority of the city. That's a bit like the firewall in front of your web front end. Then you've got the castle with a moat and an extra keep. And then probably somewhere inside here you've got another level of protection, which is literally where your crown jewels are being kept. That's great, but what happens is, if I'm a peasant living in this bit of this town, if an invading army comes in and gets past this bit of wall, and I'm living in this bit, I'm in trouble. That invading army can come and pillage. Pretty much, they've breached the gates, and then they're in. They can do whatever they want. Sure, they have another job to get into the castle, and another job again to get the crown jewels. But to be honest, I'm a peasant. I live here. I don't care about the other stuff. I'm already in trouble just because they got through this gate. In the Sony case, you can also think about, well, say it's not an invading army comes in, it's just a spy who comes in. He manages to jump over the fence, jump over the wall, and now he's wandering around the outside here. There's so many people who live in this part of the city. No one's going to look at him and go, hold on, I don't know you, are you supposed to be here? Because how could you possibly tell who's supposed to be there? So he can go around wandering for months, stealing all the executives' emails, or doing whatever he wants, before he then opens the gates and lets the army in. So that's kind of the old, that three-tier model that your IT department would have built you 5 years ago with dedicated hardware. Nowadays, of course, dedicated hardware isn't, we don't have dedicated hardware for databases or this, that, and the other. Compute resource is so cheap, you just buy commodity hardware. You're building data centers with racks and racks of commodity hardware. You don't care what it's going to be used for. However, if you give it to your IT department and say, right, well, we've bought these 3 racks of servers, we're building some web applications, if you're not careful, they're going to do exactly what they did before. They'll say, well, this rack is where your database stuff's going to go. This is where your front end, this is your back end. And we're putting firewalls between them all. Great, we're happy. So again, I do anecdotes about friends. I don't have any of my own, but another one of my colleagues was working a few years ago at I think it was actually a security-related firm. But anyway, they were very forward-looking, and they were building. They weren't quite using microservices, but they were trying to use that fast, agile development model. And he built an application. It had Apache, it had some Ruby, it had different bits of database. So he'd done what he'd been asked for. Tried to be agile, tried to be cool, and then he wanted to test it. So he said to the IT department, right, I need to deploy these. My application, how can I do that? And they looked at it and said, well, that's a web bit. Oh, that's a database. Oh, that's a back-end bit. Right, well, we'll put them here, and we'll, tell us what you need, and we'll configure the firewall rules for you. So he kind of, oh, God, okay, right. So he worked it out, and he raised the ticket. 3 days later, he got an email saying, your ticket has now been done. Your firewall rules are there. He said, oh, great, I can now test it. And that was the moment where he had the real problem where he realised he'd forgotten a bit, and he'd actually needed an extra bit in his database layer. So again, raise the ticket. This time it was probably only a day for them to put in one firewall rule for him, but eventually, he got it tested and that was fine. Other people in the department started looking at what he'd done and think, well, that's quite cool. Actually, we could reuse this bit of service that you've done here for one of our applications. And then someone else said, and each time it was, oh, well, we need to, put some firewall rules in, but this is cool. Before you knew it, it looked like this. And any small change was just driving the developers mad. Hold on, we need firewall rules to do, what the hell's going on here? And here we had a situation where the IT department was basically stifling the cool, agile DevOps type mentality that was growing in the development side of the community. So, the business chiefs, when people say, why haven't we got that new feature out? Blame IT, we're still waiting for the firewall ticket to come in. The other problem with this is what we call resource fungibility. Now, apologies, this is actually a Mesos picture, but the idea is the same for Kubernetes. The whole point of things like Kubernetes and Mesos is you can just buy lots of computing power and then leave the scheduler to use it as efficiently as possible. In this picture, there's more things here than there are here, but when the IT department initially set up the servers and put broke it all out, they put the same amount in each tier, because why wouldn't they? But suddenly you've got the point of, well, actually we've filled up this box, we've still got capacity here, oh, but we can't put one of these on there because it's the wrong side of the firewall and it's the wrong tier, it doesn't really work. So again, you're not only stifling how quickly the developers can do things, but you're wasting money. So again, that big chief, when he starts looking down, saying, well, not only is IT meaning that we can't deliver features so quickly, you're now telling me we need to buy more servers here, even though we have spare capacity over here. I just don't understand what's going on. So what does IT do? Well, they could say, fine, let's just tear down the walls. Let's break that whole three-tier thing. Yeah, everything's just computing resource. Don't care about the firewalls in the middle. You know, we'll just let you have that. That's great. Boss is happy. Developers are happy. They can start doing things quickly. Unfortunately, then you get something like the Sony situation where someone breaks through the firewall into one of these things, and now they can get everywhere within the network because there's no more firewalls in there. But you told me to get rid of the firewall. It's a problem. What can we do? And the issue is, for each of these pods, if you imagine this as a Kubernetes cluster, you've got all of these connections to all of the other pods. But the reality is, you don't need many of them. If you actually think about, as a developer, what you needed, your web front end, fine, I need to receive connections from the internet on port 80. That's it. I'm going to send some stuff out to here, going to send some stuff out to there. I'm never going to send from here to here, though. Similarly, this guy, he's like, well, I'm going to make some connections down to Cassandra, and I'm going to receive some stuff from there, but I never need to be talking to this chap here. So effectively, you can cut a whole load of those lines out, because they should never be needed. Or they are never needed. You're the developer. You wrote the code. You know they're never needed. It's not they might never be needed. It's like there is no way it's ever going to be needed. And this is what we've been working with the Kubernetes community to try and design. We want to design a networking policy for Kubernetes that allows you to sort of model this idea of developer intent and give you the security that gives you. So here, simple example, we're going to use some labels, effectively, Kubernetes labels, to say, well, this is my front end, this is my user authentication, this is my main logic, this is my database, and I'm the developer, and this is how I say these things should fit together. So, front end, well, allow from the web to be, incoming to port 80. Here, I'm going to say, well, allow from the front end, allow from user auth. Here, just allow from front end, etc. You get the idea. We're limiting all those connections. We're cutting them down as much as we can. So if we actually look at that in Kubernetes terms, as I say, this is something that we've been working with the Kubernetes Networking Special Interest Group to actually get these APIs folded in as part of the Kubernetes API. So here, the idea is that you use pod selector. So here we've got network policy, some metadata, and we're saying the pod selector is that this applies to the user auth. So this policy applies to something where the role is marked as user auth. So this is the policy for these guys here. And the policy that we're going to apply is, say, on the ingress, we're only going to allow traffic from pods which match the pod selector of role front end, so these guys. And even more, let's not just cut that line, let's really chop that line up as much as we can. We're only going to allow traffic arriving on port 8001 over TCP. So suddenly, we've cut down, those lines in that picture to, just the ones that you need, but not only just the ones you need, but only the particular ports, the particular fine-grained policy that you actually need to make your application work. And as an application developer, we can do that because it's microservices, so you know exactly what you need. When you're building those monolithic applications back in the day, people would bolt on extra features here and there, and you kind of thought, well, there's a team of 50 people working on it, so I have no idea what communication it's supposed to be doing and how it's, what ports it needs to be open and where it's going to hear from. In the model we're in now, where people are doing microservices, that's not the case. Like, no, my application is really small, it does one thing, and it needs to do that thing, it needs to talk to this other guy, and that's it. So how do we do that in Calico? So, we've got this idea of the pod definition, and you've got policy in place. I mean, say, obviously, we've been working with these guys, so we wanted to make sure that Calico would support this. And the way that we do that, we use what we call a distributed firewall, per container distributed firewall. So what we're doing, and again, we're just using a feature of the Linux kernel, IP tables, you've already got it. We're putting a firewall in place in front of every single container. And that firewall just contains the policy that applies to that container. So in the previous example, if we go back, yeah, if one of those containers is one of these guys, then the policy that we're putting in here is saying only allow traffic on port 8001 thing from other containers that match the front-end role. Now, clearly, IP tables doesn't understand the concept of front-end role because it doesn't do that. And that's where the Calico kind of magic comes in. So as part of the Calico logic, what we're going to do is as you fire up a new container with a role of front-end, and it gets its IP address assigned, Calico is then going to make sure that every host which has something where it's got some policy that is, relates to that gets updated so that it can update this IP tables rule to say, aha, there's now a new container of role front end on 172.19.5.7. So let's add a rule in here for that particular IP address on this particular port. When you destroy that container, again, Calico will go and say, that rule is no longer needed, so I'm going to scrub that out. So it's dynamic. Through plugging in via the orchestrator, we're able to dynamically pick up these changes and program take the developer intent, because as a developer, you're not worried about, I need to receive traffic from this IP address. You're just talking about services and labels. Calico's going to do the hard work of converting that into stuff that IP tables understands.
So at this point, it's a stateless firewall?
Yes. It's got connection tracking. So it's stateful in the sense of, obviously, if you're saying my firewall for my front end, I'm going to allow connections in on port 80, you kind of need to be able to send responses back to the web client as well. And that, IP tables just does that for you. It uses a thing called contract. So basically, once you're not giving the front end the permission to open up connections outbound on its own, but you are saying, if you get a connection coming in, then you're allowed to send things back on that connection. Okay, so what I'm going to do now, and I'd apologise that I'm going to do this using a video rather than doing it live, but to be honest, given that my PC's over there, I'm not going to apologise that much, because I think this has turned out to be a bit of a win. But what I'm going to do is show a demo of this network policy working with Calico. So we've been working with the Kubernetes team. This is it's an experimental feature. So the API is being worked on. It's still being worked on at the moment, and they've got it at an experimental stage. So I think at the moment it's V1 Alpha 1. I think the idea is that they want to have this fully baked by the time Kubernetes 1.3 lands in a couple of months. Obviously, it's important to get it right rather than do it quickly. But even today, you can go and download. You can go and download and try this yourself using what they've got out already as the experimental API. So what I'm going to show you is I'm going to set up a default namespace with some front-end pods. And I do realise the irony of having decried three-tier applications earlier and said, oh, that's very old hat. I'm now going to show you an example which is basically a three-tier application. But it's secured in the modern way rather than the old-fashioned way. But I'm going to start up some front-end pods, back-end pods. They'll obviously want to communicate with each other. I'm then going to start up call it a management UI. It's basically a visualization just so that we can see what's going on. And then I'm going to simulate a client. This would in reality be someone coming in from the internet, but for the purpose of the demo, it's just a client mod. So that's kind of what we want to be able to see. Management wants to be able to see what's going on and everything else. well, clients connect to front ends and front ends connect to back ends, but nothing the other way around. You know, back ends aren't able to connect out to clients, the back ends aren't even allowed to connect out to the front ends. It's all traffic going in this direction. So that's not what we want. But that's what you would get by default with Kubernetes. Yeah, you'd get the fact that everyone can talk to everyone else. So the first thing we're going to do is turn on isolation. So this was a feature that hit Kubernetes a couple of releases ago, I think, where you can basically isolate with Kubernetes standard networking. You can isolate namespaces. So you could say, well, client can't talk to anything else. With Calico, we've basically hijacked that to say, if you turn on isolation, now no one can talk to anyone. Yeah, it isolates all of your pods. So it gives you that clean slate to then start adding the policy that you want. We're then going to add some policy that allows, in the default namespace, we're going to say every pod.
Something like VLAN injection or ARP tables or so to fence them from each other, IP ranges.
It's not something that's immediately on that we're looking at. Yeah, we are looking at different requirements. Yeah, you could argue that, well, actually, one of the things you might want to do, and that has come up a lot, is saying, well, rather than isolating my between different layer 2 networks, maybe I'm just going to encrypt my traffic. So then, that will give me the confidence that people aren't going to be able to snoop and see what's going on. So that's certainly something that we're looking at. We're also looking at ways in which you could run on top of different networking, underlying networking infrastructures if you want. Because, as I say, from us, actually, the interesting piece isn't the BGP and the IP routing. It's really the policy. That distributed firewall, you could be running on an infrastructure that does give you VLANs and separates your tenants that way, but you still get the benefit of Calico by putting in place the distributed firewall rule. So again, that's something that I don't have anything to announce or say now, but it's something that we are thinking about and looking at because different people have different different requirements, particularly in the public cloud. Okay, I'm going to now say I've talked long enough. But I will be around if you want to ask me anything else after I've drunk some more. Okay, thank you.
Yeah, let's have some break, have a drink and some food, and I'll do the KubeCon wrap-up shortly afterwards, which will be like 10 to 15 minutes.
Okay.